So so this is a paper I did last year. So this was already published work. It was published in PPDD. So the paper, well, the title is Efficient Estimation of AUC in a Sliding Window. So I'm going to explain what all these terms mean, essentially one by one. So let's start with just a setup, like what do I mean here. So what we're doing actually is we want to measure a performance of a classifier. So and essentially assume that you have a classifier and you get like new items that new inputs, and you would like to classify them. Is this input well? You're doing the two-level classification problem, and you get a new sample, and you want to make a decision. Okay, so whether the sample is positive or negative. So that's your like a general setup, these new images constantly come in a stream. So consider that all these samples, you're not dealing with an offline problem where your prediction task is like is an offset setting, but data just comes online in a very rapid manner. And what you do is that you predict the value of a new entry, and then you do something with that particular value, and then after some point in time, up with some certain delay, you actually get to receive the true value of that value, and then you want to actually measure how well you actually predicted compared to that true value. This is a very standard setup in online learning. And my interest is to actually, okay, so how do you measure performance of a classifier? Because let's say your classifier performance starts to degrade, meaning that that this distribution changes somehow. Let's say you have some concept drift or some change point. Something starts to go wrong. So then you kind of trigger alarm. You need to inform the people, and then you do something with either your dictionary classifier or you inform some other things, but you have to do something. But the point here is to how to monitor their performance. So let's say that you only care about recent samples. Let's say you have a sliding window of k entries. So you only care about k last samples that have happened to you. So new sample comes in, that means that the k minus one sample, you get rid of it somehow, and then you look at the performance of your classifier over these k samples. Okay. Now, let's say if you are measuring your performance using your classifier is just a binary classifier. Your classifier is very simple. It predicts you 0 or 1, and then you just use accuracy, right? So this is how many predictions you get correct in that particular window of time. Well, normalized divided by k or something like that. Then this measuring is very simple. What you do, you just keep entries. You just remember like which ones you get wrong, and then when you remove the last k minus one entry, then you just update the values and so on. So this update is very simple to do. Let's say you want to do something complex, specifically AUC, which stands for area under the curve. So who do you? Just a question. So how many of you know what is area under the curve? What is AUC? Okay. Fair enough. Don't worry, I will give you what it is actually. So when you use AUC, you use only for a certain type of classifiers, and then the classifier doesn't give you the direct prediction; it gives you just a number. It gives a number between 0 and 1, and the closer the number to 1, the more the classifier believes that this label should be 1, and then the smaller the value be to 0, then the value will be less, will be more probably to be equal to 0. So essentially it doesn't give you a decision; it just gives you a score to each value it should belong. So that's, for example, logistic regression is one of these type of classifiers, or let's say neural networks also do that. So for these type of things, you can do two things. You can threshold it, and then you get it like, so you select some sort of threshold where the values that are above that threshold will be predicted as 1, as for the values below that threshold will be predicted as 0, and then you just use accuracy or whatever you measure for this is. And the other approach is to use AUC, which I'm going to talk about later. But the question is how to calculate AUC efficiently. Okay. Right. So let me actually give you a recap of what's actually AUC. And for that, I need to give a recap what is a rough curve. I haven't used this for a while. So rough curve, let's say that this is a rough curve. Here, the x-axis is the false positive rate, which is essentially the you have your data consists of. So you have a bunch of scores given from the classifiers and their labels. So the predicted scores, the scores given by the classifiers and their true labels, right? So each data point is just a pair of a real value number and a binary number. Okay. Now a rough curve here is just a simply so you pick a threshold. So each point on this curve represents a certain threshold, and then on the x-axis is the number of elements that have zero label, and they are larger than the threshold, normalized equal to 1. So that's what positive rate. And the y-axis is just the number of elements that are larger than the threshold and have a label of 1. So ideal classifier would have a threshold such that all the values above that threshold are equal to 1, and all the values below that threshold are equal to 0. So ideally, you want to be right at this point. But this is never the case. So by varying threshold, you will get some kind of curve happening here. And the more you go towards that corner, the better it is your classifier. And then the AUC is just simply like this area, under the curve. That's the differential AUC. It's not like the best measure, like it has its problems, but it's the most widely used for this type of classification problems. Okay.
Can I ask you a question?
Yes.
I can't help wondering. If I flip the labels,
yes.
Like sometimes it's arbitrary whether we label like a squirrel with 1 and a rat with 0 and try to distinguish between them. What happens if I switch the labels? Does the curve
it will flip, it will mirror along the 45.
Yeah, and AUC will not change, right?
Yeah, that will change. Because your classifier can't read that. Because you're predicting it the other way around.
No, but I would offer change the classifier.
Oh, no, then
I just change the labeling. And
then it will flip like this then.
Yeah, and then the area is the same. Because it's, right?
Yeah, the area is the same. Yeah.
Good.
Yeah, okay. Yeah. Right. So so how to actually like if you have this data, so you have these k data points, scores and k pairs of scores and labels. So how do you actually compute this area? So this essentially you sort it by the score, and then you can actually construct the actual line, and from that line you actually compute the AUC. So let's just look at the running time. So computing from the scratch, you need k log k times. So and k log k you actually spend on just sorting these elements. So that's the price you have to pay for it. You can do slightly better if you maintain understanding, but then you can do it in k times. So that's the exact algorithms to do it. So what I did here is that I don't compute the AUC exactly. I don't do that. What I do is that I have an epsilon. This is just user parameter. How much error I can tolerate in my calculation. So I can estimate AUC with AUC tilde, such that the error between these two values is smaller or equal than epsilon divided by 2 times the true value. So I get some approximation here out of it. So that's the negative result. But then what's the positive side here is that I can maintain this estimate as my window is running. Like over time, I can get this estimate in log k divided by epsilon I. So you can see that here's threshold. So the smaller the epsilon, the better is the guarantees, but also I will pay that in running time, and the larger it, then the larger the guarantee, then the looser the guarantee, and then what faster it is. Okay.
All right. Is that like how theoretical is that result, or do you have some experiments?
No, that's very true. That's guaranteed.
Yeah, but in practice, is it like what's the constant in the big O, like, and
well, here it's a constant, right? I mean, it depends on your implementation, but it depends on how you implement, obviously. But this one is guaranteed because there's no O whatsoever. So there's no constant thing whatsoever.
yeah.
Anyway, right. So let's look at how to actually compute AUC. So essentially, if you have the curve, so if you know like how this curve behaves, so what you would do normally when you compute AUC is just that you would make these bins. So you have this area, you just split it into bins, and then you know the width of these bins and then the height of these bins, and then you just compute it. I mean that's how it's actually computed. Yeah, that's pretty much the algorithm for exact one. It does exactly what it says. So first it sorts the entries based on the scores. C here is the height of the particular bin, and for each entry, if x is negative, then you are actually creating a new bin. So you're actually moving on the x-axis. So you add this AUC. You add that bin to your AUC, and then each time you see a positive entry, you increase the bin by 1, and so forth. So that's the easiest algorithm to compute AUC without actually drawing this curve. And then you need to normalize it such that the axis is wrong, but let's not care about this part. Right. So what's the trick to estimate this thing? And the estimation comes to, well, it's a very simple trick. In the end, what you want to do is that you don't want to count every single bin here. What you do, you just group these entries into larger bins, right? So instead of computing this blue area, what you want to compute is this orange area here. Now, the less bins the fewer bins you pick, then the less time you spend, enumerating over them. But then your approximation may go down. So you have to pick the number of bins and pick how you choose those bins a bit carefully. So for that, So for that, I'm going to insist on 2 invariants when I maintain these bins. Okay. So the first invariant number 1. I'm going to require that this difference here, this additional length that I get when, like, from the left side to the right side bin, so here this PB3, it needs to be smaller or equal than epsilon, the left side. So I shouldn't go too much up within one bin. Okay? So that this area is relatively flat, more or less. That's what it essentially says. So that's invariant 1. Invariant number 2 is that if I take this additional length of 2 consecutive bins, so PB3 this guy and then PB2 this guy, then this combined addition to the height should be at least epsilon times this side. So the left side of that bin. So that's kind of the opposite of the requirement. And what it does is that it forces the number of bins to stay small. Right? So this is what it does. So invariant 1, so it makes sure that this true AUC curve and the estimate are relatively close within the epsilon divided by 2, and then the invariant 2 will make sure that number of bins that we have is actually stay small. And why this is so? Well, if you look at the formula, so here, now if you go every 2 bins, you will actually go by, the height will be increased by 1 plus epsilon. 1 plus epsilon, so essentially after n bins, you will have 1 plus epsilon to the power of n divided by 2 because you go every 2 bins. And then this height can be at most k because you only have k samples. So this is at most that you can get, and then you can solve m out of it, and then you get log k divided by epsilon. So that will guarantee you that the number of bins stays small. So the invariant 1 guarantees that the approximation stays correct, and the invariant 2 guarantees that the number of bins stays small. Okay. Now, the question is how to guarantee that this invariance hold as new entries come in and then you're sliding your window. So when sliding a window, you need to do 2 operations. Essentially, you have to remove entry that is leaving from the window because the k plus 1 entry leaves out, and then the new entry. So you have to delete that entry from the window, and then you have to update all the structures that you keep. And when the new entry comes in, you also have to do some updates. Okay, so let's look what you have to do. So invariant number 1. Okay, so we need, first case is when you are inserting or removing negative entry. You don't really actually need to do that much. You have to do some updates, some internal updates, but actually not that much because when negative entry leaves, you actually only changing the x-axis. You are stretching your bins or you are shrinking them, but these conditions do not rely on the width of these bins. They only care about the height of the bins. Okay? You have to do some updates with the internal structure, which I'm not going to talk about it because they're a bit messy, but you don't, like in principle, the bins will stay the same. Okay, so when you are inserting or removing positive entry, well, you may actually break the invariant number 1 because you increase the height of the bin, so you actually might break it, or yeah, so you might, or if you're removing entry, then so if you're inserting a positive value here, then you might stretch this beyond this condition, so you actually may break invariant number 1. Or if you're removing a positive entry from here, then this might get small enough that it actually you break this bin again. So you have to do something. And the trick you do actually is that you just split every bin in half. It doesn't really matter where you split as long as both bins will contain at least 1 positive value. Okay. There's a little bit of math involved, so it's not a trivial result why this is true, but it's you have to take my word for it, or you can read the paper if you like. So in practice, you can show that not all bins need splitting, but it's not like only one bin that is splitting. You might need to split multiple ones. But you can also split every one of them, and then the theoretical running time will not suffer for it. You still get the same running time. But some of these bins need to be split in half. At most, it will double the number of bins, and most likely it will actually violate the invariant number 2. So you actually will get too many bins. So you have to deal with that one as well. Okay? But the good thing is, after the splitting, then invariant number 1 is correct. So you are guaranteed to have a correct result. I mean, you are guaranteed to stay within the approximation guarantee, but it might take too much a long time to compute things. Now, maintaining invariant number 2. So this is you do the following step. again, inserting or removing a negative entry, still not need to change that much stuff, because you're just stretching or shrinking the bins on the x-axis, and none of these conditions that I'm talking about, they don't really depend on the on the x-axis. But if you have positive entry, and what you're going to do is that you, after this step, after splitting the bins, you're going to look for every violation. So you find every bin that violates the invariant number 2. Well, it's actually going to be a pair because it's required to be 2 pairs. And if they violate it, then you just merge them together. And what's important is that this invariant 2 is defined in such a way that if an entry violates it, then merging these 2 bins will not violate invariant number 1. So let me show you, let me go back here, what's happening here. So let's assume that these bins 2 and 3 violate invariant number 2. So here we actually have the other way around, right? So when you merge these 2 bins, if you get rid of it, then new BB3 will be this part, and then invariant 2, well, this violated invariant 2 is actually going to be exactly invariant number 1. All right? So that's the trick, pretty much. So that's the main idea behind these 2 things. Behind maintaining these 2 invariants, you need to do some trickery to actually do this very quickly, because well, merging is quite simple to do in constant time, but splitting requires some trickery here. So especially, well, updating invariant number 1. So what we need to do is that when we're splitting the bin, like I said, we need to have we need to split the bin such that in both bins that at least one positive entry. So we need to find, given a bin, we need to find a next positive entry in that particular bin so that we can actually split that apart. And you have to do it in constant time because we have log k divided by from bins, and if you want to have proper running time, then this is what you have to do. So for that, you maintain a list. I just call it P here, capital P. This consists of all positive entries in a sorted linked list. So if you are at one particular value, you know the next one, so that gives you a constant time to find it. You need to maintain the number of negative entries between consecutive positive entries, meaning that because when you do a split, you need to know how many negative entries are in that list so that you can get the width of that particular, of the new bins. So you need to know how many negative entries there are in that bin. So you need to maintain that number. Maintaining this number is a little bit tricky because when the new positive entries the data, then you actually have to find a place where to enter it, and then you have to also compute the number of the actual. So when you're entering a positive value in this list, then you actually need to recompute how many negative numbers are between the new value and the previous values, but then you can do that with some modified red black trees. So I'm not going to go to details to that. It's quite messy, to be honest. Anyway, okay. So you just do some shifting. Okay. Let me show you some experiments that I did. So I took a bunch of standard data sets. This is from UCI repository, if I remember correctly. Train just logistic regression on them, and then just evaluate the classifier with a tiny window over the test data. I just run an experiment, and then just to show how it behaves, then I just compute AUC over the tiny window. So on the x-axis you have epsilon, so the guarantee, the theoretical guarantee that you get. On the y-axis is the average relative error that I get from the evaluation. So here's headmass, TVAs, and then mini. Actually, I don't know how to pronounce this one. mini bool one, anyway, doesn't matter. So that's the average error, and then the low row is the maximum relative error. So on average, notice that there's a multiplier here. So on average, we're doing much better than the theoretical guarantees. This is what expected. But if you look at the maximum relative error, we get quite close to the epsilon guarantee, which is epsilon divided by 2. So on maximum, we may get quite close to that guarantee, but on average, we're doing much better.
Just a clarification. So AUC is between 0.1 and 1, or
0 and 1, but it's also relative error. So actually, I divide by the.
yeah, but the epsilon is an absolute error, right?
It's relative error.
It's relative as well.
It's the approximation guarantee. It's the same epsilon that was in the.
It's but it's still kind of 0.8 is a lot in some sense that you're allowing 40%.
It's
40% deviation.
Yes.
Okay, so
yeah, exactly. So yeah. So the guarantee will be 0.40. Yeah, it's not between 0 and 100. Yeah, it's between 0. Running time. So as you expect, so the epsilon of 0.1. This is the speed up that you get when you compute like exactly, and then versus the approximation, and this is just the running time of it's the how faster is the approximation versus the exact, and as you increase the window size, then your speed up goes up, and this is as expected because one is in log k and the other one is in k. So that's expected, right? So let me just conclude. So our conclusion, so essentially, is that we're given epsilon. So this is user parameter. We will have to estimate AUC with a guarantee of epsilon divided by 2. So this is relative error, and so that's and we can maintain this estimate in log k divided by epsilon time, whereas the exact would be OK time, so in linear time. So we do a little bit faster, and this can be significant if k is large enough. So the whole idea is based on just binning the entries. So you don't compute. You just bin you just put these entries in certain bins, and then you select those bins very carefully, such that you maintain two invariants. The first invariant, which just guarantees that you get the approximation guarantee, and then the other one makes sure that the number of bins stays small. Some further observations. So some of these results are actually based on the fact that we don't have weights on the entries. That the values that you are actually that the points that you are have no weights. It's actually based on the fact that the weights are only 2 1. So this technique doesn't work exactly if you have weights, but there are some tricks that you can do, and you can get log to the power of 2k. But it's not as good. But yeah, you can do some tricks. And also, you can also reverse this approximation, because typically AUC will be close to 1, but you can also do it the other way around. And this gives you just kind of just reverse how you compute the estimation. So you actually get, in practice, you should get a better estimate by just by doing 1 minus AUC. Okay, that's it. Thank you.